Hello, my name is Carla Feistner. I'm a PhD student from the Friedrich Alexander University in Erlangen, and I'm analyzing how we can enhance mixing by introducing chaotic advection. To do so, we use particle tracking to track our particles through the chaotic fields. And this method is preferable over like finite elements or finite volume because it can preserve the fine plume structure of the plume. To analyze how well we can enhance the mixing, we use the dilution index, which is introduced here. And we have this formula of the dilution index, which is the exponential over the entropy. And you can think of this pk as the probability of a particle being contained in a grid cell k, which we have to define before that. So we divide our domain in grid cells and then we can compute these pk's. You can think of the entropy as a measure of disorder. So if all particles are uniformly distributed in the domain, then pk is the same for all k. And we have the highest entropy and also the highest dilution index, because if we put a high value in the exponential, it's still a high value. Vice versa, if all particles are in one cell, then it's like the least entropy and also the least dilution index, and everything in between is like what we want to measure with the dilution index. The challenging thing about that is that we have to choose like some grid size, and that's what I demonstrate here. So we have the same Gaussian distribution with the same amount of particles. If we use a big grid size, like that's not a very well representation of the dilution index, and also this is not a well representation. So we have to choose something in between to have like a good representation. And we can find this by plotting the dilution index over the grid size and finding the center, like where we have the least derivative. So we apply this measure for our two chaotic systems, the pulse source sink system here and the rotated potential mixing flow. We introduce the chaos by adding some source and sink structure in it. I will be very short here. So for the pulse source sink system, we have one sink and one source, and we alternatively operate them. So we push in particles by the source and then we pull out particles by the sink. But sink and source are not turned on at the same time, so it's only either source or sink. Then we have the RPM flow. So we have source in the top and sink in the bottom. Now they operate on the same time simultaneously, and after some defined time tau, we will rotate them by the angle theta. This will then produce our advective setup. To also add diffusion, we have the random walk particle tracking. So we have an advective term which is solved analytically from these two setups, and then we have the diffusive part with the diffusion coefficient sigma. And then our particles will follow the solution of the advection-diffusion equation. Coming now to our results. So we start again with the pulse source sink system. What we do, we place our particles in the beginning at a circle around the source, and then we start by pushing fluid through the source. So this circle around the source, it will grow, and each time we turn off the source and put on the sink, the circle will move towards the sink, until eventually the first particles hit the sink, and then it looks like that, where we have like this very chaotic structure where we form like this very specific structure we find in chaotic systems. If we look at the dilution index over time, which we can see here, we compare it to a baseline. In this baseline we don't have advective forces, only diffusive forces. So we start with a circle around the source and then we just add diffusion. The baseline only goes with a growth rate of 0.5, which is expected analytically, while the chaotic system can reach a growth rate far higher than that, it going up until 2 here. So going over to the rotated potential mixing flow, in this we have the same initial setup. So we place the particles close to the source at the beginning and then we just start the system. And what we find here is that we spread the particles pretty fast in a big area of the system. This area where we can spread fast is called the chaotic area, while the rest where we find less particles are the calm islands. This is a specific feature of the flow field and they reduce mixing. And by analyzing the size of these non-mixing islands, these calm islands, we can predict beforehand, before we have the simulation, if the mixing can be very well. And that's what we did here in the bottom. So we have here a measure of how well or how big the chaotic area is, how well we can mix in this area. And here where this ratio of the chaotic area is the biggest, we also find the highest dilution indexes. yes, that is my work. Thank you for listening. And